Hello everyone and welcome to the Stat Revised GCSE Physics web class this afternoon on changing atomic models. I hope you've all had a good Easter break and been revising hard. So I'm David, I'm a GCSE and A-level science teacher. I've been teaching in secondary science for about the last 18 years or so. If you have any questions as we're going through, please do pop them in the chat. I'll keep an eye on that. And if anything comes up while I'm talking, just let me know. Hi, Khadija. Welcome to this afternoon session. See if we've got a couple of other people there as well. So we're going to be looking at understanding how and why the model of the atom has changed over time. We're going to be comparing and contrasting different atomic models, and hopefully you'll be able to appreciate how new experimental evidence can lead to changing scientific models. A lot of people think that science is fixed and firm and unchanging, but in actual fact, the way science works is things develop, ideas change due to changing experiments and models that people come up with. We're not going to be covering the works specifically of Niels Bohr or Chadwick. And we'll have a look now quickly at the specifications. As always, the AQA specification seems to be the most comprehensive. So looking at how new experimental evidence can lead to scientific model being changed or replaced, mentions the Plum Pudding model there, mentions the results of the alpha particle scattering experiment, which we'll talk about. And then goes on to talk a little bit about how Niels Bohr adapted the nuclear model to suggest that electrons orbited the nucleus, which got rid of the problem whereby electrons would be thought to just spiral in and join the nucleus. So we'll come on to that in a little while. So AQA here, why new evidence from the scattering experiment led to the change, and the difference between the Plum Pudding model of the atom and the nuclear model of the atom. And finally, Edexcel, describe how and why the atomic model has changed over time, including reference to the Plum Pudding model and Rutherford alpha particle scattering experiment, leading to the Bohr model of the orbiting electrons. So atoms and the changing atomic model is the source of many a terrible teacher joke. Like, why should you never trust atoms? Because they make up everything. And protons are half glass, half full guys, because they're always positive, that kind of thing, which you can groan and repeat to your teachers at your wish. So moving on from there, let's have a look at what we already know. So what do we already know about an atom? This is a modern atomic model of an atom. And around the atom, we have in orbits these very tiny particles called electrons. Now, electrons do have a tiny mass, although you'll often consider the mass to be negligible. The mass of an electron is actually about 1/2000th of the mass of a neutron. So these electrons are whizzing around in orbits here, and then within the nucleus of the atom, so the nucleus, what we find in the center, indicated here in blue, the blue spheres, they are neutrons, and the red spheres here are, of course, protons. There's no color convention here, but quite often protons are shown as red. In your exam paper, protons are normally black filled spheres and neutrons just circles, but do keep an eye on any keys to make sure you're getting them the right way around. So anyone in the chat, would you like to offer any information that you might know already about protons, neutrons, or electrons? I'll begin to fill this in as you do and as I wait. So anything you know about a proton, a neutron, or an electron, including some of the things that I've just said. So what I haven't mentioned about protons is that they are positively charged. So protons are positively charged. They have, thank you, Khadija, they have a relative charge of +1, and that's relative to other components and particles within the atom. They're positively charged, and they're, hiya, Samaya, if I'm pronouncing that correctly. They're also found inside the nucleus. You won't usually find a proton outside a nucleus, unless, for example, you're looking at a hydrogen ion, then you might do. Thank you, Khadija. So neutrons, moving on to neutrons, they have no charge. So they are neutral, no overall charge. So they're neutral, as the name suggests. So the charge is 0. And they're also found inside the nucleus only. And then an electron. Yeah, thank you, comfort there. Eugenia is talking about the relative mass. Yeah, I'll add that information on. That's absolutely right. Let me just talk about an electron first, and I'll come back to what Eugenia has just said. So an electron is negatively charged. And we don't find electrons in the nucleus. They have a relative charge of -1, and they orbit the nucleus. Yep, relative charge of -1. Thanks, Eugenia. And what Eugenia has added is that protons and neutrons have a mass, a relative mass, which is equal to 1. And a neutron, the mass is often considered to be negligible when you that should be a G, my apologies. Negligible, you can read my scribbling there. When you study A-level physics, you begin to realize that actually the mass of the electron does have some significance, but it's 2,000 times smaller than the mass of a neutron or a proton. So hopefully all of that's okay. And thank you for all your contributions there, Samaya. Thank you for that. Yep, the mass of an electron is about 1/1840 that of a neutron. Good. So that's the modern atomic model of the atom. Now, early models differ from what we understand now, and you may be examined on your understanding of the early models, and in particular the Plum Pudding model of the atom. So, Democritus, Greek philosophers Democritus and Lysippus, they said that matter was composed of tiny particles called atoms, which could not be broken down any further. So both these philosophers stated that, I'll write it in, matter composed of tiny particles which they called atoms, which could not be further divided. Just noticing the chat scrolled up. Let's have a look. And yeah, thank you, Khadija. Atom does come from a Greek word. So it comes from the Greek word atomos. And that word literally means indivisible in English. So the word atom comes from the idea that atoms were thought to be indivisible, could not be further divided into anything smaller. It was also suggested that atoms were eternal, couldn't be destroyed, and they believed that if you cut anything up until it couldn't be cut up anymore, you would just be left with atoms. So atoms were considered the smallest, tiniest part of any form of matter. And then Dalton's model in the 1870s. Dalton came up with the idea that atoms had unique properties, and that atoms of a particular element would all be the same. They would all have the same properties. So the first thing Dalton said was that all atoms of the same element, this idea of elements, had the same properties. He also suggested that it was logical that then atoms of different elements with different properties must be different to atoms in other elements. So atoms in one element therefore must be different to atoms in other elements. Just looking at the chat here. Yes, atoms were described as, well, they were described as the tiniest particle of something that could exist. I'm not sure whether specifically at that point they were being described as spheres, but that brings us neatly on to the Plum Pudding model, which we're going to talk about next. A sphere is the most efficient shape, isn't it, for any small object in terms of surface to volume ratio. So Eugenia, you might well be right there. They may well have described them as spheres. Just think of atoms and the original ideas of atoms as being just the tiniest part of anything that you could get, something that could not be broken down into anything smaller. Hi there, Amrisa. So the Plum Pudding model and what we're moving on to now. So in the 1890s, J.J. Thomson came up with the idea of a plum pudding model. And J.J. Thomson was investigating the rays given out when you heated up a piece of metal, something called a hot cathode. So if you heat up a piece of metal by passing a current through it, then there are rays given out by that. And those rays turned out to be electrons, which were being, if you like, boiled off the surface of the metal. And he could identify those by making specialist apparatus so that he could heat a bit of metal in an evacuated glass sphere, and he could see the effect of those rays hitting a screen with a phosphorescent coating. So these he called cathode rays, and they were made of particles which must have been about 1,000th of the mass of a hydrogen atom. And this was what he discovered to be the electron. The charge on the electron is negative, and J.J. Thomson believed that atoms were effectively made up, and this is where the Plum Pudding model idea comes in. J.J. Thomson believed that atoms were made of a ball of positive charge with these negatively charged electrons just randomly dotted and distributed throughout a ball of positive charge. And that's why some students I know, particularly because it's a bit of a cultural oddity, the Plum Pudding model, perhaps more to the UK, some students struggle to sort of follow why we're talking about plum puddings. If you imagine like just a big sponge cake, and in that sponge cake you've got raisins or something dotted mixed between it, then that's the Plum Pudding model. The sponge cake itself is all the positive stuff, and the little raisins dotted throughout it, they're the electrons which J.J. Thomson had discovered and postulated were distributed throughout. So he discovered the electron by investigating rays given out by hot metals. Called cathodes. Hi there, Ravi. So yeah, a little earlier we talked about where the term atom came from. It was Leucippus and Democritus, Greek philosophers, who came up with that word. And the word atom means indivisible. It comes from the Greek word atomos, meaning indivisible. Now, J.J. Thomson said that atoms were balls of positive charge and that within those spheres of positive charge, atoms had negative electrons embedded within them. Random places throughout, electrons were embedded within them, within that sphere of positive charge. And that sums up the Plum Pudding model. That's what you'd need to say. So what is the Plum Pudding model of the atom? It's the idea that an atom is a solid sphere of positive material, and that within that solid sphere, we have negatively charged electrons randomly distributed throughout. come up with a picture here. So this is our diagrammatical representation of a plum pudding. So this is all our positive stuff. So the atom is mostly this stuff, positive mass. And that's our pudding, or our sponge cake, however you're thinking about it. And then within that, we've got these, excuse me, within that positive mass, we've got negative electrons distributed throughout. Sometimes exam questions ask you to describe something, and they often state without the use of a diagram. I'll always say as an examiner, if a student draws a little diagram and it helps them to write down what they need to answer the question, then if you want to, still draw a little diagram. Just don't make that diagram take up all of your answer space. If you need to draw yourself little prompts at the edge of your paper answer space or anything, then do so. No one's going to penalise you for doing that. If a question says without drawing a diagram, describe, then just don't draw a big diagram and label it. They want something written in sentences, in prose, or in bullet points. So hopefully you could now describe the plum pudding model of the atom. So quick time for questions now. Does anyone have any questions about the development of the idea of the plum pudding model, taking Democritus and Leucippus ideas of an indivisible atom, developing it further through J.J. Thomson's discovery of the electron, and his ideas that the atom was in fact a solid sphere of positive mass with electrons distributed throughout? That's the early plum pudding model of an atom. Any questions, please pop them in the chat, and feel free to put 1s, 2s and 3s in there, and depending on how happy you are at the moment, whether you think things have been straightforward, right, or if you're getting a bit confused. Excellent, thank you, Khadija. So we've got a straightforward there. I'll take silence as positive. So hopefully that's all okay for you all. Excellent, thanks, Shu. Oh, she's got a flat face. If there's any particular questions, Shu, that I can answer, please do ask. It could be you've got a question that someone else hasn't thought of. Thanks, Eugenia. Yeah, and a little bit of revision, a couple of little drawings, make a poster, yeah, something you can stick on your wall. This is going to be easy to remember, I think, for many of you if you do it that. It's a very visual thing. Like everything in physics, you tend to have to work out a visual way of seeing something that's really not visible normally. And so imagination plays a big part. Okay, let's have a look at a question here then. Over 100 years ago, scientists thought that the atom was like a plum pudding. The diagram below shows the plum pudding model of the atom. Then we've got our familiar diagram. We've got our negatively charged particles and the pudding part. Scientists knew that an atom had negatively charged particles. They also knew that an atom had no overall charge. So what did the scientists conclude about the charge on the pudding part of the atom? So they knew it had negatively charged particles, but no overall charge. So what did they have to say? What did they conclude about the pudding part of the atom, this part here? If it's full of negatively charged particles, what must the pudding part's properties be? So the pudding part must be positively charged. We know that an atom is always neutral. An atom is always neutral. So the charges on the electrons of the atom always balances the charge, the positive charge of the atom. And we'll go on to talk about protons in a minute. But remember, at this point, protons and neutrons had not been discovered. So scientists believed, they concluded that the solid part must be positive and the negatively charged negative electrons balanced out that positive charge. So yes, Samaya, that's what comes next. So there were the same number of protons and electrons in the model to create a neutral charge. And that's in the modern atomic model, the nuclear model of the atom. But at the point where we're talking now, where the plum pudding model was the best idea, people didn't know, scientists didn't know about protons. So when you're talking about the plum pudding model, don't mention protons or neutrons, just say that the negatively charged electrons were balanced out in charge by the positive pudding part, the positive pudding part of the atom, okay? So the nuclear model of the atom came a little later. So it was later discovered that actually atoms weren't these solid spheres of indivisible stuff, that actually they were, well, actually largely made up of empty space. And there was a very famous experiment done which proved that point. So we're going to look now at the nuclear model. So the model of the atom where an atom has a nucleus and isn't a solid sphere of positive charge with negatively electrons distributed throughout like a plum pudding, but that actually is something which is mostly empty space and has a very tiny concentrated nucleus and other things orbiting it. We'll describe those things now. So one of the most famous experiments which you will need to know about is Rutherfords Experiment, sometimes called the alpha scattering experiment. So at the beginning of the 1900s, the nuclear model replaced the plum pudding model, and it was Ernest Rutherford who discovered that some materials emit alpha particles, which is a kind of radiation. Now, those alpha particles have a positive charge. Now, along with two of his students, Geiger and Marsden, so Hans Geiger and Ernest Marsden, who often don't get credit for this experiment, he directed alpha particles, these radioactive particles with a 2+ charge, at thin gold leaf in an evacuated chamber, so in a vacuum. Now, when he fired those alpha particles at that really thin gold foil, kind of stuff you'd use to gild statues, he wanted to see what happened. So he set up a beam of alpha particles. So he had an alpha radioactive source. He put a tiny hole in a blocking material in front of that source so he could get a nice thin beam. And he directed that beam at a very thin leaf of gold, which was suspended in a vacuum chamber. The vacuum was needed so that the alpha particles didn't interact with the atoms in any air. So he just wanted the alpha particles to strike the gold. And all around the gold, you can see in the picture I'm showing you at the moment, was this thing called a scintillation screen. Now, you're not going to be asked to repeat this in an exam. This is a scintillation screen. Well, it's scintillated where particles hit it. In other words, it produced a little flash of light. In the center of our experiment here, then, we've got our thin gold foil or gold leaf. Here's our alpha source. There's an alpha particle drawn out there. There's our alpha source and our alpha beam. And all of this was in a vacuum chamber. So just to summarize what he did, and then we'll talk about what he found out. Rutherford's experiments involved directing a beam of alpha particles at thin gold leaf in a vacuum. So yeah, they fired, thank you, Eugenia, they fired positively charged alpha particles at a very thin sheet of gold. Now, this experiment came up with a number of really interesting and unexpected results. So most of the alpha particles pass straight through the foil. So here's an alpha particle at the bottom, coming from the source there, and most of the alpha particles follow this kind of path, just coming straight through the foil there and not interacting with anything. So most passed straight through. Now that in itself was very telling. They weren't interacting with any mass, they weren't interacting with any matter, which was a little odd. It could be something expected. It's a very tiny particle. Maybe it's just not interacting with anything big enough. So far we haven't necessarily disproved the Plum Pudding model, but interesting observation nonetheless. So pass straight through most of those particles. But some of the alpha particles got deflected through quite large angles. So some would disappear off there, some would disappear off up there, some even almost along the front of the gold. And remember, this blue circle is your scintillation screen. So wherever a particle hit, you could see a little flash of light, which showed us the pathway of the alpha particle after it's been, in this case, scattered by the gold leaf. So some of these alpha particles were deflected through large angles. But remember, most of them weren't. Most of them just passed straight through. It was only a very small number that got deflected through large angles. Now, an even smaller number actually got deflected by more than 180 degrees. Some of them almost coming straight back at the detector. So very few of these alpha particles were deflected more than 180 degrees. So in other words, they came backwards towards the source of the alpha particles. So very, very unexpected. Both of those are unexpected outcomes. Some deflected through large angles and very few deflected even more. And even the first one could be an indicator that atoms are mostly empty space. So why is this being deflected? Remembering that alpha particles are positively charged. What would it have to be interacting with in order to be being deflected, in order to have its path changed? Because of the presence of a positive nucleus. So there's got to be something positive concentrated in this atom, which is difficult to find because these particles were not often affected by it. So that implies that this positive nucleus of the atom is very small, but also that it is where positive charge is concentrated, because that's where the electrostatic interaction between alpha and positive nuclei causes that repulsion between the alpha particle and the nucleus. And the reason it happens so few times is simply that the nucleus only makes up a very, very small amount of the volume of the atom. So only a very small proportion of the time will the alpha particles encounter the nucleus closely enough or even directly in order to be deflected backwards. And the deflection by large angles was due to a positive nucleus, but not a direct hit. So kind of glancing near to the nucleus, near enough to be repelled. So yes, Eugenia, they discovered that the Plum Pudding model just could not be right as a result of these experiments. Really important points that came out of this experiment were the atom was in fact mostly empty space, that the mass of the atom was concentrated in a very tiny nucleus at its center, and also that that mass had an overall positive charge at the center of the atom. The negative charges we'll come to in a moment. Because the alpha particles had a charge of 2+, the deflection angles show us that the nucleus, the tiny concentration of matter at the center of the atom, must also be positively charged. So these are the conclusions that Rutherfords Experiment, along with Geiger and Marsden, came up with. So the nucleus contains nearly all of the mass of an atom. It's very tiny because most of these alpha particles pass straight through without any deflection at all. And it's positively charged because when the alpha particles did encounter it closely or even a direct hit, they were deflected. And some of those deflections were large, even turning the alpha particle around, as you can see here, with a direct approach. So in the Plum Pudding model, the beam would have been largely undisturbed, assuming the alpha particles could pass through the material which we're thinking or were thinking of as being the positive sphere. So we would have assumed the beam would be undisturbed. At the very least, we might have seen some absorption, but we would have seen these alpha particles coming straight through. The nuclear model, though, shows beam being deflected by this green positive nucleus in this case. Just going to check the chat now. So Eugenia, tiny positively charged nucleus surrounded by a cloud of negative electrons. Most of the atom is empty space. That's a pretty good description. We're just going to develop the idea of the positions of the electrons in just a moment. Good. Okay, let's move on from there. So then we come to Niels Bohr. So Bohr discovered a flaw in this nuclear model because the idea proven by Marsden, Rutherford and Geiger that the nucleus was a concentration of positive charge, it didn't explain how the electrons behaved. And the flaw that Bohr came up with was that if there were indeed sort of, as Eugenia said, clouds of electrons around the positive nucleus, then why on earth didn't they just collapse into the nucleus? So the Bohr model was inspired by this flaw, which is that the electrons should by rights spiral into the nucleus, making the atom collapse. So removing diminishing the radius of the atom overall, concentrating everything into one place. Why don't those electrons do that? Well, we have an example of a nuclear model of an atom over here. We've got one proton in the center, 2 electrons orbiting it. Now these electrons actually periodically move up and down between different energy levels, and when they move up, they move down, and when they do, they give off little photons of light. They could be gamma rays, they could be visible light, they could be X-rays or radio waves, but electrons hop around between energy levels depending on how excited they get, literally, whether they're gaining energy or losing energy here. So Bohr said that these electrons must exist in fixed orbits. So they're orbiting much like a satellite orbits a planet. They're orbiting at the right speed so that although they're attracted to the nucleus, they're never able to fall into the nucleus. They're kind of falling towards it, but missing. So Bohr said electrons existed in fixed orbits, so fixed distances around at specified distances from the nucleus. Now, you don't need to know anything about why those distances are as specific as they are. I will add, because some of you might be interested in taking physics further, it's all to do with wavelengths and the way the electrons behave as they orbit. But those, essentially, you need to know that in the nuclear model of the atom, electrons exist in fixed orbits at specified distance away from a positive nucleus. And relative to the size of the nucleus, those orbits are really quite big. So if you scaled this up and the nucleus was like a tennis ball, then the electrons would be like grains of sand orbiting maybe, I don't know, 1/4 of a kilometre away or something, if you scaled it up to that level. So most of every atom is in fact empty space, this concentrated positive nucleus and electrons orbiting at specified distances further away. Back to the model on the right-hand side, this is a hydrogen atom, of course, and we're showing the behavior of one electron here moving to and fro. I know there are 2 in the diagram, but it's meant to represent the movement of one. So a hydrogen atom will emit electromagnetic radiation, so a photon, and it emits that radiation at particular wavelengths because of the distance between the two potential paths the electron can hop between. That's a really useful feature because we can detect that EM radiation, and that allows us to analyze light from distant galaxies and stars, and we can see that emission of radiation due to that hydrogen, which is, has electrons jumping up and down and emitting a particular wavelength of light. Okay, so let's move on to our next slide, to the discovery of protons and neutrons. So far we've got positive nucleus, electrons orbiting at fixed distances away. Well, in 1910, Rutherford discovered that the positive charge of the nucleus could be subdivided into a whole number of even smaller positive particles, which were called protons. So the nucleus is not just one tiny positive lump, but many even smaller positive protons. Importantly, a whole number, you can't have half a proton. Check the chat there, Eugenia. When electrons move between shells, yep, you're quite right. When electrons move between shells or orbits, electromagnetic radiation is emitted. Yeah, they need to absorb electromagnetic radiation in order to move to a further out shell, a higher energy state, and then they emit radiation as they relax back into their usual energy states, and they sometimes take multiple paths in order to do that. Well beyond what you need to know and well beyond the scope of what we're doing now, but brilliant if you're going to be taking physics further. So in 1910, Rutherford proposed not just one positive lump in the nucleus, but many protons. And in the 1930s, Chadwick proposed that there were also neutral neutrons within the nucleus. And the neutron discovery was a lot later than the proton one. I guess because they're much harder to detect. Having no charge makes them more difficult to detect and prove the existence of. The model of the atom hasn't changed too much since. There have been some further developments of quantum descriptions, quantum mechanical descriptions by Schrödinger relating to the positioning of electrons and so on. But fundamentally, the nuclear model of the atom is now the modern understood model of the atom that we use. So we have a nucleus consisting of protons and neutrons, a very small relative to the size of the atom, a very small concentration of positive charge brought about by that combination of protons and neutrons. And then orbiting that, a relatively large distance away, we have electrons in specified distances away from the nucleus, and electrons orbit in shells dependent on the energy level those electrons have. That's the nuclear model of the atom. How are we feeling about that? So if anyone has any questions, I've gone into a bit more detail at times than I've needed. There's some nice intelligent remarks in the chat indicating to me that some of you have got a good grasp of this, but if anyone's got any questions at all, please ask. Any ones, twos or threes to give me an indication of how you're feeling is always welcome. I think Eugenia's summing it up pretty well there. Okay, right. So I'll take silence as positive. Thanks, FJ, for the one there. Okay, let's have a look at some questions and see what we can do to test what we've been covering. So there's a lot of potential answers, so a lot of potential content you could write in answer to this question. It's an AQA question from a higher paper of 2018. So scientists sometimes replace one scientific model with a different model. For example, in the early 20th century, the Plum Pudding model of the atom was replaced by the nuclear model of the atom. Explain what led to the Plum Pudding model of the atom being replaced by the nuclear model. So you've got to think back to what we've just discussed, what you've learned, what you've read. what was the most important action that anyone took to change this model? So think practically, what experiment was done? And one of the most straightforward things to start with this answer is, I think it's probably worth bullet pointing this. If you do use bullet points, always capitalize the beginning and put full stop at the end, just in case there's a QWC mark. So we can state that the alpha part, just the alpha scattering experiment will do. That will get you a mark, at least one. So the alpha scattering experiment led to that plum pudding model being disproved. A little bit of description. It wants an explanation. So what do we do in the alpha particle scattering experiment? Alpha particles were directed or fired at, say directed at thin gold foil. Most of them pass straight through. So we're just reciting all our knowledge here about the alpha particle scattering experiment to gain these marks. And this showed that most of an atom is empty space. Because there was no deflection, was there, of those 2+ alpha particles. Okay, there's obviously more we can say there. It's a 6-mark answer, so we're probably on to a high level 2 answer already, 4 marks probably for that. Let's extend that a little bit further though. Don't forget, you can download this presentation later, so although I've moved on now, you can go back and review this. You can go on to say that a few alpha particles were deflected through large angles. Showing concentrated mass of positive charge. Remember, it has to be positive, otherwise the alpha particle would have just stuck to it. So it would be deflected through a large angle. That proves the nucleus is positive, as well as being very small, because not many were deflected through large angles. So this showed a concentrated mass of positive charge. So this fundamentally there has disproved the plum pudding model, where the mass was considered to be positive and uniformly distributed positive charge throughout the spherical mass of an atom, with negative electrons scattered throughout. These experiments, the Rutherford, Marsden and Geiger scattering experiment, disproved all of that. Okay, have a look at another question here. So in the early part, this is another question. I believe this is another AQA question. In the early part of the 20th century, scientists used the plum pudding model to explain the structure of the atom. And there we've got our familiar diagram here of the plum pudding model. Following work by Rutherford and Marsden, see, Geiger's not mentioned, a new model of the atom called the nuclear model, because it consisted of a nucleus, was suggested. And we had orbiting electrons, as Eugenie described, as a cloud of electrons. That's more advanced ideas. As you do chemistry and physics at higher levels, you use different terms. But these electrons are essentially orbiting the nucleus at a relatively great distance. Describe the differences between the two models of the atom. So here we're sort of going back to a similar question to last time. We've just got to make 4 main points though. So in the nuclear model, atoms are mainly empty space. In the plum pudding model, the atom is a solid positive mass. And we need to mention the electrons, so with negative electrons scattered throughout. So that's a bit about the nuclear model. We can say a bit more. In the nuclear model, electrons orbit at specified distances. And we've already stated that in the Plum Pudding model, the negative electrons are scattered throughout. So we've made all the points we need to make there to get 4 marks. Just pointing out the key differences. So nuclear model, mass is concentrated at the center. In the Plum Pudding model, a mass is evenly distributed. In the nuclear model, a positive charge occupies only a small part of the atom, whereas in the Plum Pudding, the positive charge is spread throughout. In the nuclear model, electrons orbit some distance from the center, whereas in the Plum Pudding, the electrons are embedded in the mass of the positive charge. And in the nuclear model, most of the mass is concentrated right in the center. Most of that nuclear model of the atom is just empty space, whereas a Plum Pudding model of the atom is a solid mass. All right, let's have a look at one more. So the diagram shows the structure of an atom. We've got the nucleus in the center. We've got identified there a neutron, a proton, and an electron. In 1931, scientists thought that atoms contained only protons and electrons. Suggest, this is such an easy question, this one, really, common sense prevails. Suggest what happened in 1932 to change the idea that atoms contained only protons and electrons. What's the obvious answer? So what happened? What additional particle was discovered in 1932 is literally all they're asking you to say here. And it's even given in the question, to be fair, just above. So 1932 was the year that the neutron was discovered. Sometimes the answers they want really are that obvious. And just as a point of exam technique, if you do think, I can't be that, if you're really not sure and you're overthinking it, write what you think it might be. Just do write what you consider to be the blooming obvious, because quite often it can be. And if it isn't a complete answer, it could still gain you some marks. Okay, how are we now? I would like to ask you about describing the differences between a nuclear model and the Plum Pudding model. I'm hoping you all feel relatively confident that you could draw a Plum Pudding model, give a description of its solid positive mass, electrons scattered throughout, and then draw a nuclear model showing a concentrated, positively charged nucleus with protons and neutrons and electrons orbiting at different distances away from that nucleus. If you can do that and you can describe that in words, then you will nail the questions that come up on this. So I'm seeing a couple of ones there from Eugenia. Thank you very much. I hope our other people watching and listening are also confident. Any questions at all? Pop them in the chat now. I'm free now to answer any of your questions. So we should all be able to understand how and why the model of the atoms change with time, compare and contrast the differences between them, and appreciate how that experimental evidence from the Rutherford, Marsden and Geiger scattering experiment could lead to that changing scientific model, and generally how changing scientific evidence changes scientific ideas. Questions for me? Do pop any questions up in the chat. I'll give you a moment to think of any if you'd like to. While you're having a think, I'll just promote for you the next few web classes that are coming up. So we have a GCSE maths web class coming up on rounding, and that's scheduled for the 8th of May. These are American date formats, so that's not the 5th of August, it's the 8th of May. That's at 3 p.m. And then we've got a GCSE chemistry web class on alkanes, single carbon-carbon bonds, and that's coming up on the 15th of May at 4 p.m. And then we have a further physics GCSE web class on the 29th of May again, that'll be at 2 p.m. and that's going to be on distance time graphs. So please do come along and take part, ask questions. And as I've got no further questions now coming up in the chat, I'm hoping you're all happy. So I will wish you all a very good rest of the weekend and a good week's revising, and hopefully a successful set of exams coming up soon. So take care all, and I will see you on the 29th of May.